Training models on a workstation feels like flying business class. We got memory to spare, power to burn, and everything just works. But move the same model to production on a microcontroller, smartphone, or real-time camera stream, and suddenly you're out of runway. Your model is 3 GB, your device has 512 MB. The math doesn't lie. Now picture this: a voice assistant that lags 4 seconds before answering, a drone that stutters mid-flight due to computer bottlenecks, a smart camera that overheats after 30 minutes. These aren't edge cases, these are realities of deploying ML models in 2025. Hi everyone, I'm Nathan, a data scientist at Meesho, and in this NIAT Masterclass, we're going to tackle one of the most pressing challenges in AI deployment: how to make large language models run efficiently on constrained hardware. The answer? Quantization. It's the art and science of compressing your model, storing its weights and activations using lower precision formats like int8, FP16, and BF16 without compromising too much on accuracy. It's not new. In fact, some of the biggest tech companies have built custom chips around it. Apple's Neural Engine, Google's TPUs, Meta's LLM compression stack all rely heavily on quantization. But here's the catch: the theory is tricky, the tools are scattered, and the trade-offs are often misunderstood. That's what we are here to fix. By the end of the session, you'll be able to understand what quantization is, why it works from the hardware up to the math, differentiate between post-quantization training, quantization-aware training, and when to use which, apply quantization using open source tools like Bitsandbytes, benchmark latency, size, and accuracy across different formats, and interpret the trade-offs clearly. And here's what we'll build: a quantized version of ResNet 101 optimized for fast image classification, a compact variant of Llama 3.2 tuned to handle LLM prompts with fewer resources, a clean, reproducible benchmark pipeline to measure latency, accuracy, and size so you can justify your decisions in production. Because here's the truth: AI's future doesn't just belong to the most accurate models. It belongs to the ones that can run anywhere. Let's get started. Alright, let's peel back the layers of quantization, because this is where the real magic happens. Now, you've probably heard this term thrown around a lot, especially if you've been working on deploying models to mobile apps, drones, wearables, or even trying to speed up LLMs. But here's the real question: what are we doing when we quantize a model? Let's break it down. Quantization is simply the process of reducing the number of bits we use to represent numbers in a neural network. In most deep learning models, we work with tensors, which are big blobs of numbers like weights and activations. These are usually in float 32 precision, meaning each number takes 32 bits of memory. That's fine when you're training on GPUs in the cloud, but not so great when you're trying to squeeze that model into an edge device with limited power and memory. So what do? We shrink those numbers. We represent them using fewer bits like float 16, BF16, or even down to int8, which is just 8 bits per number. Let me walk you through this visual. On the top here, we've got our original weights in float 32. You'll notice some big values here: 228.1, 209.3, and even -300.3. These are precise but expensive to store and compute. Now watch what happens when we quantize. We introduce a scale factor, in this case 2.48, optionally a bias, which is 0 here. We multiply each float by this scale and then round it to the nearest integer within the int8 range of -128 to +127. The result? The same matrix of weights, but int8, smaller numbers, smaller memory, and faster computation. This is called uniform affine quantization of the same scale across the matrix. And we compress everything proportionally. And the best part, this quantized version is about 4 times smaller and much faster to run, especially on specialized hardware. So why is this so important? Because by lowering the precision, we unlock some huge benefits. Number 1, reduced memory footprint. With each weight and activation now compressed, your model is lighter, way easier to fit on an edge device with, say, just 512 MB of RAM. Number 2, fast inference. Arithmetic gets faster when you're dealing with smaller numbers. Matrix multiplications, convolutions, all get serious speed boosts. This means real-time predictions from video streams faster chatbot responses, and even live LLMs on laptops. And finally, energy efficiency. Fewer bits leads to fewer memory transfers, and that leads to lower energy consumption. For battery-powered devices like drones or smartwatches, that's a game changer. Think of it this way. It's like switching from raw photos to a compressed JPEG. Sure, you lose a little bit fidelity, but in return, you gain massive reduction in memory consumption, portability, and ease of use. And the trade-off? It's more than worth it, especially when the JPEG looks pretty great. Now that we understand what quantization is and why it matters, the next question is, how do we actually do it? Let's explore the different techniques and strategies developers use today to quantize models without sacrificing too much performance. So how do we get our models from float 32 down to int8? There are two broad strategies. Number one, Quantisation-Aware Training, or QAT. QAT is like sending your model to quantization school. We introduce fake quantization operations during both forward and backward passes of training. So the model learns what it feels like to operate under reduced precision. Here's a diagram of QAT in action. On the left, forward passes use fake quantization like Q and DQ blocks. This is done to simulate quantization errors from rounding and clipping so that the model learns to deal with these errors without actually doing the quantization. And on the right, the gradients in the backward pass simulate reduced precision. The model adapts its learning to be more robust to the eventual quantization. The benefit? The model learns to deal with the errors better, which leads to improved accuracy. The downside? It's training intensive and training can take longer. Think of it like rehearsing with weights on before the real performance. Number two, post-training quantization. This is simpler. You simply fully train the model in float 32, then compress it afterwards, like zipping a folder. Here's the workflow. Take a pre-trained model, use a calibration dataset to understand activation ranges, and apply quantization. Quick, no retraining required. But because the model wasn't trained with compression in mind, it can lose some accuracy, especially on sensitive domains like NLP. So far, we've talked about how quantization reduces the precision of weights and activations. But what exactly are these lower precision formats we keep mentioning? Let's put them side by side and understand their strengths. Float 32, the gold standard for training. High precision but heavy. Think of it like the DSLR of numerical formats. Float 16, half the bits. Still decent precision, supported by most modern GPUs via tensor cores. Great for accelerating training without too much compromise. B-Float, or short for Brain Float 16. This one is special. Developed by Google, it keeps the dynamic range of float 32 while sacrificing some precision. It's incredibly stable, perfect for TPUs and large-scale training. That's why you'll find it behind the scenes in systems at Google and Meta. int8, the go-to for deployment. Smallest and fastest. It's what we use on mobile devices, edge chips, and NPUs where memory and power are limited. Unsigned int8. It has slightly different use cases, especially when hardware acceleration supports it. Now that we've seen the formats from float 32 down to int8, it's time to ask the real question. How do we actually fit a wide world of float 32 weights into a tiny int8 box without making a mess of the model's performance? Let's start with the problem. Real-world models don't play nice. They come with weights that can swing from -100 to +1000 or even beyond. But when we quantize int8, we're squeezing everything into a fixed box, just -128 to +127. That's a tight squeeze. Something's got to give. To solve this, we use calibration. Now, what is calibration? Think of it like adjusting the camera's exposure. You want the brightest parts and the darkest shadows to fit within your image without blowing them out. In quantization, histogram-based calibration scans the distribution of weights and activations, then selects a scaling factor that maps the useful range into int8, while minimizing the number of values that get clipped. Let's take an example. Suppose your model weights between -150 and +900, but the int8 can only represent -128 to +127. So, we scale the weights down and divide by a factor of 7.2. Clip anything beyond the limits, and round the result to the nearest integer. The goal? Preserve as much meaningful information as possible with minimal distortion. Floating point refresher. Why int 8 struggles? To appreciate why this is hard, we need to understand how float32 works. Float32, the default format in most models, has 3 parts. 1 bit for sign, 8 bits for exponent, and 23 bits for mantissa, the fractional precision. This combo gives us a huge dynamic range courtesy of the exponent, high resolution thanks to the mantissa, but most importantly, non-uniform spacing. You get more precision closer to 0 and less as you move outwards. Now compare that to int 8, 8 bits only, no exponent, no mantissa, just a sign bit. It's evenly spaced integers from -128 to 127. That means no dynamic scaling, no fine-grained precision, and no forgiveness for outliers. So when we force float32 into int 8, we're essentially flattening a mountain range into a parking lot. The steep cliffs become gentle bumps, and anything too tall gets chopped off. Quantization isn't just a format switch. It's a careful trade-off between fidelity and efficiency, and calibration is what helps us strike that balance. Ready to explore what kinds of errors this introduces? Let's move to quantization errors next. Alright, so we've seen how float32 gives us a rich representation with a wide dynamic range, but squashing that into int 8 comes at a cost. Now let's talk about that cost. Quantization errors. What do we lose? Whenever we convert high precision weights to lower precision formats, we introduce quantization errors. And while these might sound harmless, they can significantly affect the model's accuracy if not handled right. Let's break down the 3 main types of quantization errors. Number 1, clipping. Some weight values fall outside the representable range of int 8, that is -128 to 127. What happens to them? They get clipped, gone. Imagine 250 becoming 12, the information is lost. Number 2, rounding. Here values is simply rounded to the nearest representable integer. Float 12.7 becomes 13, float 12.4 becomes 12. Not a big deal in isolation, but across millions of weights. Finally, saturation. Too many extreme values can overflow the representable range, pushing everything to the boundaries. Think of this like trying to describe shades of color using just 8 crayons. You can't recreate a sunset accurately if you round, clip, and compress. Same with model weights. Now the real question. How do we know if our quantization is working well? Here are 3 metrics to watch. Number 1, accuracy drop. How much performance do we lose post-quantization? For example, from 76% accuracy down to 74%. Number 2, size reduction. We often shrink models by 2x to 4x. A 400 MB model can drop to under 100 MB. And finally, latency gains, faster inference. Especially critical in real-time applications. Think milliseconds saved per request or more queries per second in cloud setups. Hardware support. Who makes this work? Of course, this magic doesn't work in a vacuum. You need hardware that supports low precision operations. Let's take a look. NVIDIA GPUs support both float16 and brain-float16 via tensor cores, super useful for training and inference. Google TPUs, both brain-float and int8 extensively, especially in production models at scale. Apple Neural Engine, optimized for int8. This is what powers features like Face ID and on-device Siri processing, edge devices, Raspberry Pi, Jetson, and even microcontrollers. Many now support int8 for blazing fast local inference. So the question becomes, is your model compatible with the hardware it will run on? If yes, quantization can bring serious acceleration with almost no compromise. So quantization isn't just about compressing models into neat little zip files. It's about adapting intelligence, making models nimble enough to run anywhere, on the cloud, on your phone, or inside a drone. And in the next section, we will get our hands dirty. We will quantize ResNet 101 for image classification, Llama 3.2 for text generation, all using open source tools and just a few lines of code. Ready? Let's dive in. Before we tackle LLMs, let's start with a simpler, more controlled playground: image classification. In this lab, we'll quantize a pre-trained ResNet 101 model and test it on Flowers 102 dataset. We'll explore three things: how quantization affects accuracy, how much model size shrinks, and how much speed up we can actually get. Let's jump straight into the code. So here we have libraries Torch, Vision, and Bitsandbytes. Now this Bitsandbytes is what we are going to primarily use for quantization. So let's run this cell. Now that our libraries are installed, we'll go through the code. So first, we import all the libraries that we require, which are primarily from Torch and Torch Vision. Then we use a Flowers 102 dataset, which consists of 8,000 images and 102 classes. We import the dataset as such using the datasets library. We split our dataset into train and test sets with an 80-20 split. Then we load our dataset into train loader and test loader, and we initialize the number of classes. So these are the class names for the 102 flower classes. Next, let's visualize how the image looks. So here is an image of Hipposteum, or I don't know if I'm pronouncing this right. Next, let's actually load a ResNet 101 model. So we'll be using image 1K weights with the ResNet 101. And over here, as you can see, we are actually removing the last layer and replacing it with random weights and 102 classes. And then later on, we will attach this model to the GPU. So this device is initialized as our GPU device. After that, we will go through training of this model on this dataset. We will train this model for 7 epochs. And after we train our float32 model, we will do quantization and convert it to FP16 and int8 data types. Now our model training is done and we have trained it for 7 epochs. As you can see, the 5th epoch actually has the highest test accuracy score, but we will take 7 for this exercise. Of course, you can play around with the number of epochs and see which one works best. Let's again visualize the image from the test loader this time. So we have an image of Siam tulip. Now let's see the accuracy of all 3 models: float32, float16 and int8. So we will run this on our test loader dataset. So as you can see, we have the accuracies for float32, float16 and int8, and surprisingly int8 actually has the best accuracy here. But this could be also because of the dataset. But as you can see, the accuracies are almost in the same range, so you can consider all of these models to be pretty much equally accurate. Now let's test the latency for all these models. So we'll test the latency on a single image. As we can see, the latency of FP32 and FP16 are almost in the same ballpark at 11 milliseconds, and int8 takes 110 milliseconds. Now the reason why int8 takes 110 milliseconds is because we have initialized our int8 to use CPU. So over here, as you can see, we have used float32 and we have done post-training quantization on float32 model over here to float16. And as you can see over here, we have actually again initialized the ResNet 101 weights with ImageNet, ResNet 101 model with ImageNet weights. We've changed the last layer and initialized it to the number of classes. we have created the last layer as a linear layer. Then we have loaded the state dictionary of the earlier float32 model that we have just trained. We have put the float16 model to device and created half precision of it. So essentially this float32 model is now half precision and it becomes float16. However, this GPU does not support int8 natively. To support int8 on this GPU, we would have to use a specialized library like ONNX runtime or TensorRT to actually get this running on GPU. So instead, I have just initialized this model to CPU or loaded this model to CPU. That's why we can see the latency difference over here. These two models, FP32 and FP16, are actually running on a GPU, whereas int8 is running on CPU due to issues with library constraints. Now, int8 is typically a tricky integer data type and quantization type. So, getting support on this on the open source community will be hard. So, let's consider float32 and float16 as our competitors, as we know that we can run this on GPU. Okay, so now that we've seen the individual latencies for a single image, let's check if we batch these images in batch size of 1, 8, 16 and 32. Over here, when we did see the individual latencies of FP32 and 16, we saw that the latency was in the same ballpark. And theoretically, we learned that quantization not only reduces size, but it also reduces latency. Over here, when we do the batching, we actually notice that in fact, FP16 takes only 0.68 ms per image or 1400 images per second. And the same FP32 runs only at a speed of 625 images per second. So we get a speed up of 2.35x when converting FP32 to FP16, but only provided we have a batch size of 16. You can take a look at this graph. So over here we see that the actual speed up only starts at batch size 16, and at batch size 8 it's still only a 1.04%, which is in the same ballpark. Now why does this happen? Well, if you run it at a lower batch size, memory doesn't become the bottleneck. There's a lot of overheads that actually happen and play in the background that causes latency. Now, when memory becomes the overhead, you can actually observe this latency drop. So this is especially apparent with smaller models like ResNet. But as we go for larger models like Llama, you would see the latency drop immediately from FP32 to FP16, even at batch size 1. So over here, we observe that FP16 takes less memory than FP32, and the total memory reduction is about 13%. But this is also because that we have run twice the amount, 2.3 times the amount of images per second. So let's finally do the cost calculations, right? So at FP32, for a ResNet 101 model, it is typically about 44.5 MB. Now running it at a FP32 precision, we need essentially 4 bytes, right? Because each byte is 8 bits. So for FP32, which is 32 bits, we need 4 bytes. So that's why I multiply that by 4. And then since this is in MB, we multiply by 10 power 6 to get 178 MB. Similarly, at FP16, we would only need 89 MB of memory. Now let's use these values in calculation to actually see how much our cost would be. So FP32 at, let's say, batch size of 16 or 32 is about 600 or 570. So let's take at batch size 16. So at FP32 we can run 625 images per second. At batch size of 16, at FP16 we can run about 1470 images per second. So if we divide this number by 1000, let's assume that we need to process 1000 images per second. We round it up to the nearest whole integer and we get that we need 2 models to satisfy this and we get 2 GPUs to run this model. Similarly, we only need 1 GPU to run an FP16 model. So let's calculate the cost. So let's assume that an L4 or a G6 X large is about $8 per hour. And we need to run this 24 hours, 365 days a year, right? And we'll assume our conversion rate from dollars to Indian rupees as 87. So this is the cost running this for a year on FP32. And we need 2 instances. Similarly, for FP16, we just need 1 instance. So I will run this code. So for an FP32 model, we will actually burn around 12 lakh rupees per annum. And for an FP16 model, we'll only burn 6. So the amount that we save annually is about 6 lakhs. So here we can see that there is some real world impact in cost savings and memory consumption and latency as well. But there's a few things to keep in mind. When your model size is small, you need to do batching to actually get the goodness of quantization. And integer 8 data types and other sort of data types actually do run into technical issues when you're trying to run it on a consumer GPU. You would need specialized libraries such as ONNX runtime, TensorRT or Triton to be able to run an int8 model on this GPU efficiently. So let's summarize what we just learned. We learned to quantize FP32 into FP16 and int8 using post-training quantization. We learned that int8 is a little tricky data type to work with practically. And we also saw that batching is required for smaller models to actually get the latency gains. We've just seen how quantization shrinks and speeds up a computer vision model like ResNet. But now it's time to tackle something much more formidable: large language models. And here's the catch. LLMs are a different beast altogether. Why are LLMs special and so hard to quantize? Let's start with the scale. LLMs like Llama or GPT models often contain billions of parameters. At float 32 precision, that's hundreds of gigabytes just to store the weights. You can't just throw that onto a Raspberry Pi. Even high-end consumer GPUs may choke. So we turn to quantization. But then, new challenges emerge. Challenge 1. Sensitivity to quantization errors. In ResNet, a little rounding error might only shift a pixel or 2, but in LLMs, the attention mechanism is like the brain's working memory. Tiny perturbations can cascade. An error in early layers of self-attention can ripple forward and destabilize the entire output. Challenge 2. Layer-specific dynamic ranges. Here's another hidden complexity. Some layers in LLMs have weights between minus 0.1 plus 0.1. Others might go from minus 300 to plus 800. Trying to quantize them all using the same scale, you either clip aggressively or lose precision. That's why per channel or per layer scaling is critical. So to summarize, ResNet, a homogeneous structure, image data, much more forgiving. And LLMs, complex architecture, heterogeneous weight distributions, and much more fragile to errors. But the good news, there are techniques designed specifically to overcome these challenges, and that's what we're here to explore. So we know quantizing LLMs is hard, but how do we actually do it in practice? Let's walk through the 3 state-of-the-art approaches that bring LLMs from the cloud closer to your laptop. Number 1, post-training quantization with error correction, or GPTQ. If you've ever wished for a smart quantizer, this is it. GPTQ performs per channel quantization, meaning it doesn't just apply one scale across the whole matrix, it adapts to each channel. It also applies error correction by minimizing the differences between the original and the quantized weights, almost like compensating for its mistakes as they happen. No retraining required. Just take your pre-trained model, run GPTQ, and you get surprisingly accurate results. This is especially useful for llama-style models where fine-tuned accuracy is critical. Number 2. LLM intake. Mix precision in the right places. Here's the problem. Fully quantizing attention layers often leads to unstable behavior. Here's the solution. Don't fully quantize. Be selective. LLM int8 takes a hybrid approach. Use int8 for heavy-duty matrix multiplications where speed really matters. Accumulate results in float 16 to preserve numerical stability. You can think of it like a hybrid car. You get the efficiency of an electric using int8, but the fallback of a combustion using FP16 when you need it. This hybrid method allows large language models like GPT and Llama to run with massive memory savings and minimal accuracy loss without blowing up attention. And finally, GGUF, CPU optimized format from Llama CPP. Now let's talk about deployment. GGUF is a highly optimized file format designed for running quantized LLMs on CPUs. Here's why it works so well. It stores quantized tensors in a binary layout that is cache optimized. It also includes quantization metadata like scales, offsets, and block size, all baked into the same file. It works seamlessly with Llama CPP, a C++ implementation for Llama that can run on 7B, 13B, and even 70B models on local machines. The result? Smooth LLM inference on laptops, desktops, and even Raspberry Pi class CPUs without needing a GPU. Together, these techniques unlock real-world LLM deployments even in constrained environments. In the next section, we'll move from theory to practice quantizing a Llama 3.2 model and benchmarking it live. We warmed up with vision models. Now let's apply quantization to a real LLM, Llama 3.2. The goal here, understand how quantization impacts size, speed, and language quality in real-world NLP workloads. Let's jump straight into the code. So here, I have taken the liberty of running this notebook because LLMs are quite slow and running this notebook in real time would take a long time. So first, we have already installed the packages that we require. As you can see, we are using Unsloth, we're using Bitsandbytes and the other transformers and regular packages that we normally use, along with Torch. So why are we using Unsloth? Well, here Unsloth actually allows us to download the LLMs directly from Hugging Face without any sort of permissions. So I took the liberty of using Unsloth here. So over here, we have taken an FP32, FP16 and FP4 models directly from Hugging Face. Also, we load these models directly in its native floating point integer like FP32, FP16, and we also load it in 4 bits. So after we load the model from Hugging Face, we check if the model is actually running on a GPU. As you can see, all 3 models are running on CUDA, which indicates they are loaded on GPU. After that, we use a Google BoolQ dataset. So what this dataset really is just a true-false dataset given a passage. So given a passage, we need to determine whether this passage, the question to this passage is true or false. So for example, I have run individual passages from this dataset using FP32 model, FP16 and FP4. So here is the passage. Here is the response that the LLM gave and here is the ground truth. As you can see, for this passage, the ground truth response is different from the LLM response. So FP32 has gotten this wrong, whereas FP16 and FP4 have both gotten it right. We can also see that the latency of FP32 model is 1.5 seconds. The FP16 and the FP4 model is both around 0.4 seconds. But why are we observing FP4 to be the same latency as FP16? Again, this goes into the specialized GPU that we use. Over here, we are using an L4 GPU, which doesn't run FP4 formats optimally. To run FP4 formats optimally, you would need an H100 GPU. So over here, let's actually get the precision and accuracy numbers along with the F1 score and recall. So I have run this on the Google BoolQ dataset and have compiled the results. So over here we have a classic classification report for FP32, FP16 and FP4. You can observe the results. The average accuracy is for FP32 is 75%. The macro weighted accuracy is 74 and then weighted average is 75. Similarly, if you check for FP16 and FP4, you will notice a small drop from 75 to 74 and similarly from 74 to 72. Macro average also drops by 1 point and then subsequently 2 points. Weighted average also drops by 1 point and just another point for FP4. We have also measured the average latency for all the models running on this test dataset. So you can see that FP32 is quite slow. It takes about 1 second on average. FP16 runs at 340 milliseconds, and FP4 runs at about 330 milliseconds. So let's do a small exercise by calculating the cost and of running these 3 models. So let's assume a Llama 3.27b model. So this means it has 7 billion parameters. So to run an FP32 model, we would need 28 GB. How do we come to this calculation? We take the number of parameters, we multiply it by 10 to the power 9, as a billion is 10 to the power 9, and we need 4 bytes, which make 32 bits. Similarly, 2 bytes make 16 bits and half a byte makes 4 bits. So we get the memory that is required for all the 3 models. Then we take some average cost estimates for A100 machine, which is 40 GB, an L4 machine, which is 24 GB, and a T4 machine, which is a 16 GB machine. We also have its cost per hour. Then we calculate for if we have to keep these machines running for a year. So before that, we have to see if we can run this FP32 model on an L4 machine. Since we require 28 GB, we need an A100 machine, which is at least 40 GB. For FP16, we need 16 GB, and this perfectly, and we wouldn't be able to run it on a T4 because there will be certain overheads. So we would have to choose an L4 machine, which is 24 GB. And similarly for FP4, we just need 4 GB of memory. So this can comfortably run on a T4 model. But again, we had seen that in theory, we cannot run FP4 efficiently on a machine that is not H100. But over here, if we are okay with this latency, we can continue and run this FP4 on a T4 machine. So let's calculate the cost per year. So we have 24 into 365 into $4 per hour into the conversion rate of dollars to rupees. Similarly, for FP16, we will use an L4 machine, and we will and this will be the running cost. Similarly for FP4. And if we do the calculation, if we change from a A100 to an L4 machine, we would save about 24 lakh rupees annually. And if we move from an A100 to a T4 machine, we would save about 25 lakh annually. Now, of course, if we have to run an FP4 model efficiently, we would have to run it on a H100 machine, which is even more expensive than an A100. So we will not take that into consideration here. So let's summarize what we just learned. We were able to load an FP32, an FP16 and an FP4 model from Hugging Face directly using Unsloth. Then we measured the accuracy and the latencies for each of these models. We saw that the FP32 model performed the best, the FP16 the second best, and the FP4 the third best, with minor difference in accuracy and F1 scores. Then we calculated the cost of running these models on the most optimal machine. And we saw that running an FP4, even if it is unoptimal, still gave the best cost benefit. So if you're okay losing 2 to 3 points in accuracy for your task, you would choose an FP4 model over here. Before we wrap up, let's zoom out and connect everything that we've learned to what's happening in the real world. Quantization isn't just a clever lab experiment or a topic for academic papers. It's the unsung hero behind some of the most important AI systems today. Smartphones. Take voice assistants like Siri, Alexa, or Google Assistant. Every time you say, "Hey Siri," your phone doesn't fire up a remote server. It uses an int8 quantized model on device to recognize wake-up word instantly. It's fast, private, and efficient, all thanks to quantization. Self-driving cars. In autonomous vehicles, timing is everything. Object detection must happen in milliseconds. You cannot afford to miss a stop sign or delay braking for a pedestrian. Quantization allows these models to run at edge on embedded GPUs, where size and speed are non-negotiable. IoT devices. Whether it's a smart camera, fitness tracker, or smart thermostat, these tiny devices don't have the luxury of GPU or cloud access. They rely on microcontrollers and on int8 or BF16 quantized models to detect motion, understand commands, or adjust temperature. Cloud inference at scale. Now scale that up. Imagine running a billion GPT-style computations per day. A 2x speed up from quantization doesn't just mean faster responses, it means millions in cost savings for cloud providers, whether it's on your wrist, on the road, or in the cloud. Quantization is what makes real-time, scalable, affordable AI possible. It's no longer a nice to have. It's a cost of entry for production-ready AI in the modern world. We began today with a deceptively simple goal. Shrink the model, not the power. And look how far we have come. You now know we started with what quantization really is and why it's absolutely critical for real-time, real-world AI. Then, we learned the difference between post-quantization training and quantization-aware training. Then, we learned how to compress ResNet 101 and Llama 3.2, benchmark them, and get real metrics. Want to go deeper? Here's how you level up. Try quantization-aware training on your own models. Get that extra performance edge. Explore mixed precision inference. Blend int8 and BF16 to get the best of both worlds. Most importantly, quantize a model you actually use, whether it's for vision, speech, or language. See the difference for yourself. Quantization isn't just a back-end optimization. It's becoming a core skill. If you're an ML engineer, data scientist, or infra builder, this is your edge. Because the future of AI, it's not just bigger models. It's smaller, faster, and cheaper, and it runs everywhere. From data centers to edge devices, from research to production, from ideas to impact. So keep experimenting, keep building, and let's keep compressing.